Okay, so we're starting a new chapter. We'll be doing this chapter 17 for a few days. In this chapter, we're going to look at the reactions of conjugated pi systems. So the first example of those that we'll look at are called dienes. What does that mean? Diene. Yeah, two double bonds. And we're going to specifically be looking at the conjugated type, but let's look at all the categories of dienes that are possible. If you have two double bonds, they could be isolated, meaning there's a double bond, and so it's sp2, sp2. But then there's an interruption in that conjugated system, or that pi system rather. This is an sp3. So what that means is that, why is that an interruption? Why does that interrupt these two bonds? Why are they isolated from each other? There's no ability for electrons to resonate through here because we don't have an unhybridized p orbital. So the key thing with these sp2 hybridized carbon atoms is that there is an unhybridized p orbital that's sitting on that carbon atom. And normally electron resonance can occur. We can delocalize electrons through pi bonds, through p orbitals. But in this case, electrons can't be delocalized through an sp3. Why is that?
There's no empty p orbital.
Well, there are sp3 orbitals though. Why can't the sp3 orbital have resonance with the unhybridized p orbital?
Not in the same plane, like they're not in plane.
Exactly, they're not in the same plane. So this is a tetrahedron, and the sp3 orbitals are, in this case, they'd be pointing out one down probably and one up actually. But they're not in the same plane. That's the point here, is they're not overlapping with these p orbitals. So electrons can't travel through them, whereas can't exist through them. It's like a node, and the electrons can move through here. It's not exactly a node, but it's kind of like that. So that's what we call an isolated diene or triene or polyene or whatever. We also have something called a conjugated pi system, and this is where the different pi systems are able to delocalize electrons through one another. And that's because of a continuous arrangement of sp2 carbon atoms giving unhybridized p orbitals being next to each other. So in this case, we have the ability to have resonance through that. And that's what we'll be focusing on, are the conjugated pi systems. Now, there's another category of dienes. This is called accumulated diene. So we have two enes. Now we have over here a carbon atom. What's this hybridization of this carbon atom at the end?
sp2.
This is sp2, so there's a pi bond there. And we have this carbon is hybridized also as sp2, so there's a p orbital. Now what's the hybridization of this carbon atom? In the middle. This is an sp. So there is a p orbital that's unhybridized going like that, but there's also another p orbital like so. And actually, if we drew this correctly, well, let's look at this. We've got, this is linear, so let's say this is going up and down, so this is an H over here. So we're going up and down, this is a CH3. These would be going one in the front and one going back, right? They have to be orthogonal to each other. So in fact, the p orbital, the sp2 system that's here, is overlapping with this, right? And these p orbitals are overlapping here. So it's a little bit more complicated, but would you say that the electrons are delocalized through that whole system or not? Is it possible that they could be? Yeah, because we have a continuous array of p orbitals available for the electrons to sort of go do resonance through. And we can draw resonance forms through that. So those are the three types of dienes. Here's a picture of kind of what we were just drawing, but with colors. So the orbitals, this is artwork from the book. So they drew actually, I think it's the same, they drew the accumulated pi system the same way. So you got overlap here, and then overlap on the orthogonal pi system, and then conjugated, and then the interrupted one. So why are we talking about these these atomic p orbitals? Well, because we're going to be focusing on those, and specifically we're really looking at some interesting reactions that have a lot to do with if there's delocalization through those p orbitals. Here are a few examples of molecules that have conjugated systems involving heteroatoms. So it doesn't have to be all carbon. We can have heteroatoms. But it requires that heteroatom also allow the electrons to delocalize through it, right? Just like a carbon atom would. So let's take a look at this. This is a alpha-beta unsaturated ketone. We've been talking about how to make those and reactions of them. And it turns out these are also conjugated. So what I want you to do is try to draw the the p orbitals across this thing, showing where they would all be delocalized, like we were just doing on those other drawings. And then, of course, there has to be one also on this oxygen, right? And that's not really a good drawing for it. Like, I probably could have drawn a lot better than that, but you get the idea. There's an sp2 orbital on each of these atoms. So the electrons can delocalize through the entire enone. And that's why we can get that resonance form that shows that the beta carbon is electrophilic, right? Because we can draw resonance structures through that. Do the same thing for this molecule down here, this tricyclic nitrogen heterocycle. So we see there's an isolated pi system over here because of the sp3 and sp3. But then nitrogen is also sp2 hybridized, so that it has a ability to delocalize electrons through it because of the unhybridized p orbital. So this is an example of another conjugated pi system. So let's look at some chemistry involving these. This is how you could make, this is an example, just one of how you can make a diene, a conjugated diene. If you take, do an elimination, if you take an alkyl halide, either a 1,2 dihalide or an unsaturated alpha halide, we could use a sterically hindered base to do an E2 elimination to synthesize these dienes. You have to use the hindered base, obviously, because otherwise you get nucleophilic substitution on the bromide. So we want to do an elimination, not a substitution. So that's basically how you'd make them. But just so you know, most dienes are commercially available. Synthesizing them isn't, well, I shouldn't say most. Many standard ones are available. Modifying them is a relatively simple matter. Now we have to talk about the conformation of these things, of conjugated dienes, because it turns out that really important reaction we're going to study requires a certain conformational, there's a conformational preference for one conformation of diene. So we need to understand what's going on here, what everything looks like. So if we look at a diene, we can draw two conformations on paper. And this is where I'm rotating this bond here to draw what we call the S-cis conformation and the S-trans conformation. What do you think that S stands for? We know cis and trans, right? Cis and trans, we usually, when we see a cis and trans, it looks like this is cis. And, sorry, that's trans. My brain is still waking up. This is cis. So we have trans and cis. So why do you think these are called S-cis and S-trans and not just like cis and trans?
There's two double bonds.
Okay. Well, what if I drew that? It's two double bonds. Is this cis or trans? Trans. What's the S mean? Is this really cis or trans? Can this change from trans to cis? Can I just go like this and say, oh well, it's in equilibrium with this? Are those interconvertible? No, because we have a pi bond here that's locking it. It's conformationally restricted. Is this conformationally restricted? No, because we get a dog wagging its tail. This thing can just spin around and around. Because this is a sigma bond. This is not a pi bond. So the S stands for sigma. Sigma cis and sigma trans. And so really, they can be converted between one another. And I wanted to show you the arrangement of the p orbitals in both cases for the ones I've drawn here. So we've got, if we put these on here, they can all line up like this. That's still conjugated, right? Because all the p orbitals are lined up with one another, like this, and this. Right? Same thing here. They're all lined up, so the electrons can still delocalize. But imagine a situation where, well, I guess here's a good question. Are there any other rotational conformations that might be possible? Are these the only two, or are there more? Well, what about, there are a lot more. There's an infinite number of other conformations. There's one, for instance, what if this was in the plane of the paper, but then sticking out, right, of the plane at it, it's hard to draw that, but sticking out at us, there's a CH2, right? So there's like a double bond in here. So these p orbitals are in the plane. But here, they're not aligned up anymore. The p orbitals aren't lined up because there's a 90-degree angle. So like this is going up and this is going up. But these guys aren't arranged anymore, so there's no overlap. You could also imagine it going back, and there's an infinite number between those possibilities. So why do you think I only drew these two? Why didn't I just draw some of the others? Well, the reason why, it has to do with this energy level diagram. So first let's look at the two minima on this. Right? We've got S-cis, S-trans. These are the two minima on this energy curve. And there's an activation barrier in going from one to the other. So why do you think, first off, that the S-trans is lower in energy than the S-cis?
There's less electron density together.
Yeah, well, there's a steric argument, is I think what you're trying to say, right? So like, let's look at S cis. Oh, bang, right there. There's a bumping of electron clouds from these two, right? So that raises its energy level profile. I mean, you can think about that over here as well. These two are eclipsed, right? Those two are eclipsed there. Now, if we look at the S trans, this is HA, HB, HA, HB. HA and HB are no longer eclipsed anymore in the trans. They're staggered. Well, they're not really staggered. They're anti to each other. Yeah, they're staggered. You can think about that. If you're looking, your mind's eye is looking here, the things are 180 degrees apart. And then we also minimize that torsional strain that results from these two, or the steric strain rather. So steric strain and torsional strain that you can relieve by going into the S trans. So S trans is actually the lowest possible energy conformation possible for a diene. That's the absolute minimum for it. Whereas, is the S cis the absolute maximum? No. What's the absolute maximum? Well, it's somewhere up here, right? Somewhere in the translation from the S cis into the S trans. And that's why it has to go through this high energy barrier to get over it. So there's a barrier to getting to the S trans, or rather going back. If we wanted to go back to the S cis, right? You have to go uphill and then end somewhere at a higher energy. And this is probably that conformation that I was showing you earlier, where there's like a 90-degree. It's really hard to draw. I guess we could go like that. Right, where there's like a double bond here. Or there's like a 90-degree orthogonal interaction. So halfway between when this starts rotating in this direction. That's higher in energy. So why, though? Why is it higher in energy even than the S trans? Is it because of sterics? Is it because of torsional strain? I mean, if we move this thing, let's imagine we rotate this bond. Any way we rotate it, we're going to be relieving the steric strain, right? We're taking away this steric, we're moving those away from each other. Shouldn't it go down in energy? Why?
Are we breaking the delocalization between the whole system?
We're breaking the conjugated pi system by taking those p orbitals away from each other. So this is actually kind of like that stabilization you get from aromaticity, right? Same idea, except we're breaking it. It's almost like breaking a small aromatic system, even though it's not aromatic, it's linear. Same idea though. So that's the results of breaking those conjugated pi systems. Thing to keep in mind though is that the S cis conformation is higher in energy than the S trans. So now we're going to review also, while we're talking about this stuff, we need to think about the electronics. That was kind of the structure of dienes. Now we're going to talk about the electronics a little bit. I want you to try to draw the molecular orbitals. Yeah, question?
I don't know. I feel like there's something that's not quite making sense back on the slide, because I feel like if you took the system and you actually rotated that bond the way I'm thinking of it, wouldn't you have them out of phase? You have like the blue trying to line up with the red?
Which one drawing? Are you talking about this one or this one? Or somewhere in between?
Both, really. If you took one and then tried to flip it, wouldn't you have them out of phase with each other?
Well, right now
are
you saying that they might be out of phase?
No, right now they're in phase.
Yeah.
The drawing.
Right, but
But I'm imagining if you actually took that signal bond and tried to rotate it like that, would you have the red facing up?
Yeah, exactly. That's what I'm talking about. That's the breaking of the conjugated pi system. That's when you're going from here to here. You have to twist this bond and break the conjugated pi system. So the red would be pointing out at you.
But once you got to the S trans, wouldn't the red be pointing up?
The red would be, but again, those are just relative color changes. So like they're they don't have to stay those colors. They can change phase when you flip them.
Okay.
Don't worry about those color changes. That's just trying to show you. I see what you're saying. They're still overlapped. That's the important thing.
Okay.
When they're overlapped, the phases can change. Okay.
Okay.
It's not stuck. But when they're not overlapped, then they can't be in phase. It's kind of like why hyperconjugation can happen. So, like, we know about anti-bonding molecular orbitals, right? Like, those are usually out of the opposite phase sign as your bonding molecular orbitals, but they can still provide a stabilization because they're there. Same idea. Don't get hung up on the colors too much. So here we go. Let's talk about MO theory. I want you to, this is practice, try to draw the molecular orbitals Psi1 through Psi4 for 1,3-butadiene. And 1,3-butadiene again is just this. Okay, so first off, why do we have four? These are molecular orbitals again. So these are MOs. And they're all going to be sitting on top of the same molecule, and we're just trying to sketch them. We're using Huckel's MO theory for this, meaning we're going to forget about all the sigma bonds. Why can we think like the sigma bonds when we're doing this? Because those have molecular orbitals as well. We're only worried about the pi bonds, though. If we look at this energy curve, all the pi bonds are going to be higher in energy than the sigma. All the sigma molecular orbitals will be down here. Why can we say that those are unimportant for chemistry? I'm only worried about these high energy orbitals. Well, we're only worried about the high energy orbitals because that's where all the chemistry happens, with the electrons that are highest in energy. So those are the ones that are most likely to react with other things, because they're higher in energy. So that's what we're talking about, high energy ones. Huckel's MO says that if you have a conjugated pi system, the highest energy electrons are in pi molecular orbitals. Why are there four of them?
So, four different ways they could be in or out of phase with each other.
Well, the number of molecular orbitals is equal to the number of atomic orbitals that we combine, right? And we have four molecular atomic orbitals. So if we look at the atomic orbitals that we're talking about combining, we're combining a p orbital, like p1 with p2 with p3 and p4. If we assume those p orbitals exist, they're on an atom, so we call them atomic orbitals. If we take all the atomic orbitals, yeah, we can combine them in four different ways. and therefore we get 4 molecular orbitals. That's why we have the same number. It's because we can only combine them in 4 different ways. Because they have 2 phases with them, right? Either positive and negative phase. So the lowest energy one is when they combine all in the same phase. Right? They're all lined up. And then the next highest one, we're going to have a node right down the middle of it. So that happens when you combine them across phase like that. And then in psi 3, we're going to have 2 nodes. So when you're trying to figure out where the nodes go, try to be symmetrical about it. Like that. And then the last one, we have 3 nodes. So the number of nodes to the number of MOs minus 1. Okay. So that's what the molecular orbital picture looks like. Now what we have to do is populate this thing with electrons so that we can figure out what the highest occupied molecular orbital is and the lowest unoccupied molecular orbital. Have we talked about those before? Highest occupied and lowest unoccupied yet? HOMO, LUMO? We'll talk about those as we go. So there's this thing called HOMO and LUMO, and we're going to use that a lot in this chapter. So now we have to figure out how many electrons to fill this thing up with. To do that, what you want to do is look at the number of pi electrons. So the electrons that live in pi orbitals and pi bonds. Only those. So then we have 2 electrons for each double bond. So we have, in this case, a total of 4 pi electrons. And we're going to follow Huckel's rule for filling these things up. We're going to, not Huckel's rule, I'm sorry. We're going to follow the off-bow principle and fill this thing up from the lowest to the highest. So we've got 4 electrons, we'll populate it, we pair them up, and then go to the next highest level. And that's what it looks like. That's where this molecule, if we think about it, we have, in the lowest energy orbital, we have electrons that are delocalized over the entire molecule. 2 electrons. That means that 2 electrons are really on the whole molecule, not at any one particular place. It would be kind of like saying we have this sigma bonding framework and there are 2 electrons through the whole thing. Okay, and then the next highest energy one, where are the electrons? So this one, they're all delocalized. Are they delocalized on the next highest one? Not really, right? They're sort of isolated from each other. So the next highest one, it's kind of like we're saying, oh, they're here, and then they're not sharing between the 2 sides, but they're over here also. So it's kind of like they're not delocalized. That's why it's higher in energy. So we can say that they're sort of on the terminus, right? And they're stable there. But then on the next highest one, it's kind of like saying the electrons are in the middle and then on the ends. That's the only way I can really describe that. Right? And then on the highest energy one, they're just localized on each individual atom. It's like they're here, they're here, they're here, and they're here. They're fully localized. That's the highest energy one. Okay. Now, what we can also do is define something called frontier orbitals. That's what the HOMO and the LUMO are. What the HOMO stands for, what highest occupied molecular orbital, that's HOMO equals highest occupied, MO. And LUMO is lowest occupied, MO. These are called frontier orbitals. Sometime in the late 70s, a Japanese gentleman named Fukui, Fukui, who was awarded the Nobel Prize for rationalizing chemical reactions in terms of frontier molecular orbitals. He said that every reaction can be defined in terms of interactions between the highest occupied molecular orbital, in this case, psi2, and the lowest unoccupied molecular orbital. Now, there's some very interesting chemistry you can do thinking about orbitals in that sense. Why do you think that those frontier orbitals are important in terms of chemical reactions? If you think about it, the highest occupied molecular orbital, those are going to be the highest energy level electrons. Those are the ones that are most likely to go somewhere, right? To form a covalent bond. And where will they be able to go to? Some other molecules are lowest unoccupied. Some empty orbital that has the lowest energy. That's why it's an interesting theory. They go from, basically we're saying that electrons are going to go from somewhere over here to here. Or to here. But not like from here to like way up here when they could just go here. That's the idea. So that's the idea with frontier molecular orbitals, and we're going to see some interesting things. I want to call your attention right now to think about this. The end carbons. So very important to pay attention to the termini here. We're going to see that. How do I want to explain this to you? Let's look at the ends here. Notice here that the ends of these two are symmetrical, right? They both have the phase is symmetrical. We're going to call that garad. This is an advanced thing. Garad, meaning symmetrical. Meaning the ends, if we think about them, they have the same phase. We can ignore the middle part. Now, psi1 and psi3 are both garad, right? We can put a G next to this one as well. However, psi2 and psi4, those are ungarad. They're not symmetrical. You're going to take inorganic chemistry and then 300 level inorganic. That will come back in full force. Something that organic chemists don't say as much, garad and ungarad, but it's a nice tool for looking at the symmetries of these things. Hold that in your mind for now. Okay, so here's an interesting thing. Frontier orbitals got pretty exciting when people realized you could rationalize photochemistry in terms of that. There are reactions that are photochemically allowed and reactions that are photochemically disallowed. And stereochemistry is also impacted by photochemistry. And what happens, we think in photochemistry, is that, or in other things, we have things called the ground states and excited states. So normally a molecule is in what we call the ground state, and for example, in this particular example, the HOMO is psi3. And when light impinges on this molecule, it's possible to excite an electron into a higher energy, into the LUMO, which then becomes the new HOMO. Right? We change the symmetry. This is no longer the lowest unoccupied molecular orbital. it's now the highest energy occupied molecular orbital. And what that does is it changes the symmetry of the orbitals. So it went from is this Garad or ungarad? Garad, and it went to ungarad. Now a reaction can happen, and it's interesting the possibilities that arise. You'll see. Here's a question for you. So all this stuff, so it turns out the gap between these orbitals can be measured. There's an energy gap between these two things. We know what it is. We can figure it out for any molecule. How do you think we would go about doing that? Right, and when it excites, it absorbs energy, right? So we can do absorption spectroscopy or emission spectroscopy and get a picture of the energy levels. So there's an experiment called UV visible spectroscopy, a machine where you can take a molecule and put it in this thing and basically shoot light at it, either in the visible spectrum or the UV spectrum. It will absorb and produce, go into an excited state, and then drop that back down and do an emission. But that absorption part is actually what we measure. And you get a spectrum that shows you where it absorbs. And you can see multiple absorptions most of the time between different excited states. And you can put a picture together and determine what energies you would need to excite this thing with so that it can do certain reactions. This is the basis of luminescence as well. One thing I'll mention is what I want to ask you. What do you think happens to the gap in the energies between these orbitals as we increase the number of p orbitals that are involved in conjugation? So let's say we start expanding this bigger and bigger. What's going to happen to the energy gap here?
And then decrease.
Yeah, it should decrease. And why do you think it should decrease?
Just
Guessing 50.
Because there's more electrons to move back and forth.
For more electrons, we can think about if this energy gap is decreasing, we're increasing the stability, right? Because it's lower energy transitions. Why would expanding the number of electrons in p orbitals that are delocalized stabilize the electrons in the orbitals? Why would it lower their energy? Well, because we're increasing their delocalization, right? Delocalization is a stabilizing effect, and therefore the gap would get lower and lower, smaller and smaller. Anyway, it's kind of an interesting thing. But we'll talk more about that because it is pretty interesting. I'll summarize that. More conjugation. Equals lower energy transitions. And so the color changes that you see become different as well. As the gap in this decreases, we get longer and longer wavelengths of light. Right? More and more red, less and less blue. And eventually it becomes brown. Okay. Now here's a little brain puzzle. Here's a reaction of a conjugated diene. It's an electrophilic addition. And if you conduct this experiment at 0 degrees Celsius, we'll get this thing called the 1,2 adduct as the major product. The minor product is what we call the 1,4 adduct. But at high temperatures, the trend is reversed. Major product becomes the 1,4. What I want you to do is try to construct an energy diagram. Why this is happening? explaining this result. So you have to decide which product is more thermodynamically stable is the first thing. And how are we going to figure that out? What's that?
The major product's gonna be.
Well, we have two different major products. So we have a major product at 0 and we have a major product at 40. So which major product is the one that's more thermodynamically stable, do you think? And what's, yeah, sure, so what, why do you think it's made?
Is the location of the double bond, it's more saturated at that spot.
That's a really good one. So the double bond, it's more substituted, right? So the double bond is this is a di-substituted double bond. This is only a mono-substituted double bond. It's internal, it's definitely a more stable. It's like the Zaitsev double bond. So 1,4 is definitely more thermodynamically stable. We can also see that in the data. At 40 degrees Celsius, the one at higher temperatures, one predominantly is the more thermodynamically stable. But it's better to look at that double bond. So this would be the 1,4 adduct. And then the 1,2 adduct is somewhere above that. Now, are both of these going to have the same transition state? No. One should have a higher energy and one should have a lower. Is there any way, there are multiple ways of figuring out which one. Anyone have any ideas on how we could figure out?
The one that requires more energy is the one that's transition state, right? Because you have to get over it higher.
Yeah. So let's look at 0 degrees Celsius. We're providing less energy at 0 degrees Celsius, right? Less kinetic energy is available. And at that point, we're forming more of the 1,2 adduct, right?
So it's gonna have a
Lower transition state for the 1,2 because we don't need to provide as much energy to it. So the 1,2 should be lower in the transition state than the 1,4. You can also think about that in terms of what it was made from, right? The 1,4 and the 1,2. The 1,2 is going to have, these both have carbocation intermediates, right? We're not talking about the transition state, but we're talking about the intermediate. So there's going to be an intermediate here that I left out of the energy curve, which we can put over here somewhere. We can say there's a carbocation, and there are two different carbocations, right? There's one that's secondary, and there's one that's primary, right? So primary carbocation is going to be higher in energy than the secondary. And the transition state to that one should be also higher in energy. So this would be like the primary carbocation going to the 1,4, and then this would be the secondary. So why am I showing you all this? Well, I'm trying to show you the difference between kinetic control and thermodynamic control. And these dienes undergo reactions that allow both. So it's something to be aware of. Which one is kinetic control, the cold one or the hot one? So kinetic is always the one that's faster to get to. Kinetic equals faster, equals lower activation energy, right? That's the kinetic product. You think kinetics is fast, right? It's something to do with motion. Now the thermodynamic product, I'm not sure if this is kinetic. The thermodynamic product needs energy, needs heat. Or needs heat because it has a higher activation energy to it, even though it's more thermodynamic. Okay, that's thermodynamic product and kinetic products in summary. So here's a reaction for you to try your hand at. I didn't give this in your notes. So try this out real quick and see if you can predict the major and the minor product, or sorry, the major product for each one. Just the major. And I'll give you a little hint. Okay, so we're going to favor at 0 degrees C the 1, 2 or the 1, 4? Zero degrees C, we should favor the 1, 2. Okay, and then we have to decide where does the nucleophile go, the bromide? Is that going to go in the primary position or the secondary position? Secondary. And the H goes over here. Okay. Now it's opposite case at 40 degrees Celsius, we're going to favor the 1, 4. So what you want to do is just draw this carbon skeleton. And then we're going to migrate the double bond from the termini to the middle like that. So we'll make one double bond from 2. And the bromide, is that going to go on the tertiary position or the primary? Tertiary. So we'll put a bromide here. Okay. And the H goes on the end. Okay.
I thought the one that ran at 40 degrees would be no substitute.
The one at what degrees?
40 degrees.
40 degrees is the more substituted double bond. Let's see.
Because you did them exactly backwards.
Oh, that's because we have a difference. Well, so we put, I drew this one wrong. This one's correct, right? Because we have the dye substituted. We're not going to move the bond. We have to move the bond this way. Here, though, this one should be, yeah, I neglected that. My bad. So in this case, we're going to add, let me draw the carbon. The bromide should go in the tertiary position. I think so. We're going to add, H is going to go here. And let's see, H is going to go here, and the bromide is going to go there. And we'll end up, it's either this. Let's look at the two possibilities. We are either going to make this one or this one. Right, those are the two possible products. And we're cold. So we're going for the kinetic product. What did you draw this one, Reese? Let me see what you drew.
I drew that one originally.
The first one or the second one? Second one. Think about it. So we're cold. So we're not providing enough energy to get through the transition state that would allow the secondary carbocation. So this one would be correct. Okay, so we're done for today. Next time we'll talk about this stuff and it deals all the reactions. And then lab today, you'll be starting, you have 2 to 3 weeks, or as much time as you need. It's an unknowns identification lab. Don't be put off by the fact the document is like 30 pages long.
47.
47, yeah, it's long. But it's not like you're going to be having to write all that stuff down. That's just there for reference. It's like a reference book for how to go about doing your unknown identification. The most important part is like 4 pages long. The first part of it tells you what you're going to do, basically. So you're doing quantitative tests. Don't worry that it's that long. It's a reference for you. You've looked at it? Yeah. It's not as big a deal. It just seems overwhelming at first.